Dear students, in the last lecture, we discussed the development of torque in an induction machine. And we have seen that the torque is developed as a consequence of the interaction of the rotor currents with the rotating magnetic field. And the torque is developed in the direction of the rotating magnetic field relative to the rotor. We also observed that the rotor currents create a field of their own, and this field follows the stator rotating magnetic field with an angle of 90 plus phi behind the stator rotating magnetic field, where the angle phi was defined as the rotor power factor angle. So we therefore have a rotating magnetic field on the stator and a rotating magnetic field on the rotor, and we can therefore also think of the torque development as a consequence of the interaction of the stator and the rotor fields. And in fact, it is through the rotor field and its attendant changes that the stator knows the rotor and hence transfers the power demanded across the air gap of the machine. We shall now proceed to derive an expression for the power developed in an induction machine. We know that the EMF induced in the rotor winding per phase is given by E2 is equal to 4.44 F2 phi N2 K W2, and at standstill S is equal to 1 and the frequency of the rotor induced EMF F2 will be equal to F1, and therefore EMF induced per phase of the rotor at standstill will be equal to 4.44 F1 phi N2 KW2. Let's number this equation as 1, and we shall henceforth use the term E2 to denote the EMF induced per phase of rotor at standstill. And therefore the EMF induced at any other value of silp S, the EMF induced per phase of rotor will be given by S times E2. Now this EMF acts on a rotor circuit which will have a resistance and a leakage inductance. And the leakage inductance in the circuit manifests as a leakage reactance. Per phase, and we know that the reactance is equal to omega times L, which will be equal to 2 pi FL, and the reactance therefore depends upon the frequency. Now let R2 be the resistance of the rotor circuit per phase, and let X2 be the leakage reactance of the rotor circuit per phase. Therefore, the rotor current per phase will be given by I2 as a phasor will be equal to the EMF in the circuit is SE2 divided by the net impedance of the rotor circuit per phase, which is R2 plus JSX2. This equation as 2. We can represent equation 2 by an equivalent circuit in which we have the EMF SE2 acting on a rotor circuit of impedance R2 plus JSX2. So let's draw the circuit. SE2 this will be R2 here, so JSX2, and the current flowing in the circuit will be I2, the rotor current per phase. This is figure 1. It's the circuit representation of equation 2. In this circuit, I2 is a self-frequency current. Self-frequency current produced by a self-frequency voltage, frequency EMF SE2 in a rotor circuit of impedance R2 plus JSX2 per phase. Now the power associated with the rotor circuit of figure 1 is the rotor copper loss, which can be written as rotor copper loss PCU2 will be equal to I2 square R2, and it's the copper loss per phase of the rotor circuit. Equation number 3. Now, since the rotor is rotating, it develops mechanical power. And therefore, the total power associated with the rotor circuit per phase will be given by total power associated with the rotor circuit per phase will be given by PG will be equal to PCU2, the rotor copper loss per phase, plus PM, the mechanical power developed per phase. PG in this expression is known as the air gap power. Air gap power, because this power is received by the rotor from the stator through the air gap of the machine. Now, as far as the equation 2 is concerned, it can be rewritten as I2 will be equal to, if we divide the numerator and denominator by S, we have E2 in the numerator divided by R2 by S plus J x2. Let's number this equation as equation 5. And this equation 2 can also be interpreted by a circuit in which we have the EMF E2 acting on a circuit of impedance R2 by S plus J x2, and the operation that we have performed on this equation does not change the magnitude and phase of the current. The current in the circuit is still the same. Let's number this figure as figure 2, and this figure is the circuit interpretation or circuit representation of equation 5. Circuit representation of equation 5. But one thing can be seen from this circuit. Now, as far as the circuit is concerned, the EMF acting on this circuit is E2, which is a line frequency induced EMF. And hence the current I2 can also be thought to be a line frequency current, which is produced by a line frequency induced EMF E2 in a rotor circuit of impedance R2 by S plus J x2. Let's write it down. I2 in equation 5 is a line frequency current produced by a line frequency induced EMF E2 in a rotor circuit of impedance R2 by S plus J x2 per phase. Now we see that by doing the operation on the equation number 2 to get equation 5 results in the rotor current whose magnitude and power factor angle remains unaltered. And we know that the only way the stator knows the rotor is through the MMF produced by the rotor currents. And therefore, if the rotating rotor of figure 1 is replaced with a stationary rotor of figure 2 having the same number of turns, the MMF will remain unaltered. The rotor MMF will remain unaltered, and therefore the stator will not be able to differentiate the two rotors, and hence the power transferred across the air gap will remain unaltered. Now we see that the total power received by the rotor circuit of figure 2 is appearing only as the rotor copper loss, and hence the air gap power will be given by Pg will be equal to I2 square R2 by S. Equation number 6. This is the total power received by the rotor of figure 2. It's making use of equations 4 and 6. Equations 4 and 6, we have Pm plus PCU2 is equal to Pg, which gives Pm as Pg minus PCU2, and if we put in the values, we'll have I2 square R2 by S using equation 6 minus the rotor copper loss, which is given by I2 square R2, which can further be written as Pm equal to I2 square R2 can be taken out into 1 upon S minus 1. Let's number this as equation 7. Now, this equation can further be written as Pm can also be written as, if we evaluate the quantity within brackets, we can write it as 1 minus S times I2 square R2 by S. And we know that this portion is equal to Pg, and hence it can be written as 1 minus S times Pg. The air gap power, in terms of the air gap power, the mechanical power is expressed as 1 minus S times Pg. And similarly, we can write an expression for the rotor copper loss per phase as, since we know that it is I2 square R2, it can therefore be written as S times Pg. Equation number 9. This analysis was carried on per phase basis, and hence for a three-phase machine, the air gap power will be given by Pg will be 3 times the air gap power per phase. Therefore, it will be 3 times I2 square R2 by S. And Pm in a similar way will be equal to 3 times I2 square R2 into 1 minus S by S, which can therefore be written as 1 minus S times Pg. Now, when we write Pg for a three-phase machine as 3 times I2 square R2 by S, the mechanical power in terms of Pg is still given by the same expression 1 minus S times Pg. And in a similar way, the total rotor copper loss will be equal to 3 times I2 square R2, which will be equal to S times Pg. Now, having obtained the expressions for the power developed, we can write the expression for the torque developed as torque developed. First, the electromagnetic torque developed, which is also known as the gross torque. Electromagnetic torque developed or the gross torque. It will be given by Te will be the power developed, which is Pm, the mechanical power developed, divided by omega r, the rotor speed. And Pm, as we have already seen, is given in terms of the air gap power as 1 minus s times Pg, and we know that the rotor speed is given in terms of the synchronous speed as 1 minus s times omega s, and hence we can write expression for the electromagnetic torque also as Pg by omega. The shaft power will be lesser than the total power developed. PSH will be lesser than the total power developed because there will be friction and windage losses. So PSH will be PM minus PFW, where PFW is the friction and windage loss, and hence the shaft torque will be given by TSH will be equal to PSH by omega r. So these are the expressions for the net electromagnetic torque developed and the shaft torque. Let's now solve a numerical problem. A three-phase, four-pole, 1440 rpm, 50 Hz induction motor has star-connected rotor winding having a resistance of 0.2 ohm and leakage reactance of 1 ohm per phase. When the rotor is energized at rated voltage and frequency, the rotor induced EMF at standstill is 120 volt per phase. Calculate the rotor current, rotor power factor and torque at the time of starting and at full load. Part B of this problem. If an external resistance of 1 ohm per phase is inserted in the rotor circuit, calculate the rotor current, rotor power factor and torque at the time of starting. So let's solve this problem. We'll first write down the data that has been provided. It's a 4-pole machine, P equal to 4. NR is given as 1440 rpm, frequency F 50 Hz, and the rotor is Y connected. The rotor resistance is given as 0.2 ohm and the leakage reactance at standstill. This is the rotor leakage reactance at standstill per phase, which is given as 1 ohm. And at standstill, the EMF induced per phase of rotor is given as 120 volt. And you should remember that under running conditions for any other value of SILP, the rotor induced EMF will be S times E2 and the leakage reactance will also change to S times X2 under running conditions. Now, therefore, let's solve part A of this problem. I2, the rotor current as we know is given by SE2 divided by R2 plus J S times X2, because for any value of the rotor induced EMF per phase is S times E2 and it acts on a rotor circuit whose resistance per phase R2 and the reactance per phase under running conditions will be S times X2 as has been said previously. So this is the rotor current per phase. Now at the time of starting, the SILP S is equal to 1 and hence the starting current I2ST, we'll denote it by I2ST. ST means starting current. It will be equal to S here is 1, so E2 divided by R2 plus J, again S is 1 into X2, and if we put in the values it comes out to be 117.67 ampere at an angle of minus 78.7 degrees, and hence the rotor power factor will be given by cosine of this angle, which is equal to 0.196, a very low power factor. The torque developed uh, in general is given by, as we know, it is Pm by omega r, which is also equal to Pg by omega s, and Pg we know is equal to 3 times I2 square R2 by s. Then in the denominator we have additional term omega s, and hence at the time of starting the torque developed will be Te st, means starting torque will be 3 times, we'll put it here for I2, we'll put I2 st, so square R2 divided by s is 1 into omega s. This is the expression for the starting torque. And now let's first calculate the synchronous speed omega s, which is 2 pi ns, which can also be written as 4 pi f by p, which comes out to be equal to 50 pi radians per second. The starting torque therefore will be obtained by substituting the values for different variables, which is equal to then which comes out to be equal to 52.82 Newton meter. Now at full load, let's calculate the full load slip of this motor. S will be equal to ns minus nr by ns. Nr is given as 1440, and ns, let's calculate ns also. Although we have calculated the synchronous speed, we have calculated it in radians per second. Here we'll calculate in rpm, so that we can substitute here to calculate the slip. Now it will be ns, as we know, is 120 f by p, which is equal to 1500 rpm, and the corresponding slip therefore will be equal to 0.04. Hence I2, the rotor current under full load conditions will be given by SE2 divided by R2 plus JSX2. We'll put the full load slip value for the full load slip here, which is 0.04. So after substituting the values, the full load current comes out to be equal to 23.53 ampere at an angle of minus 11.3 degrees, and the corresponding power factor, rotor power factor, will be equal to cosine of this angle, which is 0.98, and the torque, full load torque, will be equal to 52.87 Newton meter. Let's compare the different values under starting condition and full load condition. We have seen that I2 starting current is 117.67, and the full load current for this motor is just 23.53 ampere, and we therefore see the starting current is too high compared to the full load current. It is as much as almost 5 times the full load current, and the power factor, rotor power factor angle at starting is very poor, 0.198, and at full load it is high, which is 0.98, and the starting torque is of the same order as the full load torque. Now in the second part of the problem, we are asked to calculate the starting current, the rotor power factor, and the starting torque when an additional resistance of 1 ohm is inserted in the rotor circuit. Therefore the rotor circuit resistance will be equal to 1 plus 0.2, which is 1.2 ohms, and corresponding to this, if we put in the values as we have done in part A of this problem, you may do the calculations yourself. The starting current comes out to be equal to 76.82 amperes, and the starting power factor, rotor power factor, it comes out to be 0.768, and the starting torque is 135.25 Newton meter. Therefore what we see with higher rotor resistance, we can compare it with this value. The starting current gets decreased with higher rotor resistance. The starting power factor, rotor power factor, it is improved, it's quite high. This is the reason why the rotor current gets decreased, because the power factor improves. And one more advantage we see with higher rotor resistance is that the starting torque is increased. It's quite large compared to the starting torque when the rotor resistance is the actual rotor resistance 0.2 ohms only. So what we have concluded from this problem is that with a higher rotor resistance, the starting current is lowered and the starting power factor of the motor will be improved, and the starting torque is also increased. So with this we'll conclude this lecture. Thank you.